All right, so let's just jump straight into the first chapter that we'll be going over. So this will be chapter 1 from the Tro book. And this chapter is sort of almost like a primer chapter. A lot of this you probably will have heard before. Some of it maybe you haven't. So it'll be a good mixture of both of those two things. So it'll be some things as a refresher and some things that will be brand new. But this will kind of set up the chapters that we go over in the future. So the basic principles we'll be talking about here, just what is matter, types of measurement, and sort of the types of problems we'll be solving in this class. So just the basic types of things we'll be talking about. Okay, so we're going to start by just talking about atoms and molecules. Okay, so we want to talk about that the physical properties of matter are determined by the chemical and the physical properties of the atoms and molecules. Is what we're saying here is that something you can hold or something you know of or can feel. Okay, so the properties of matter. Okay, so what I'm describing there is matter. The properties of something you can hold and touch and something that exists. Okay, so whether it be water or, your table or something like that, a chair. Okay, so some piece of matter, the properties of that matter are determined by the chemical and the physical properties of the atoms and molecules that then make up that matter. So for instance, something like a carbon dioxide or carbon monoxide molecule. Okay, so it's made up of carbon atoms and oxygen atoms. Okay, when those come together, we form a carbon monoxide molecule, and that has some properties based on the stuff that goes into it. Okay, and we'll discuss a little bit later that even though it's made up of carbon and oxygen, it doesn't quite take on the properties of carbon. It doesn't quite take on the properties of oxygen. It actually has something different. Okay, so that would be an example of a molecule, maybe. But if we're talking about something like just an atom, okay, so we would just have the carbon atom. So if we had something like graphite, for instance, the properties of graphite will be based on the properties of the carbon atom. Okay, so the things that make up something are what determine its chemical and physical properties. So for instance, atoms. Okay, so what is an atom? Well, we sort of inherently know this. Okay, but an atom is a submicroscopic particle that make up matter. Okay, and we're going to say that atoms are the building blocks of elements and molecules. And we'll talk about what is the difference between an element and a molecule in just a little bit. Okay, so what about molecules? So we talk about molecules, we're going to talk about two or more types of atoms coming together. Okay, so our example here would be carbon monoxide. So carbon monoxide would be an example of a molecule. Why? Because it has two or more types of atoms. Okay? Or two or more atoms. It doesn't have to be two or more types of atoms. It could be the same one, depending on what we're talking about. But if we have more than one atom coming together, more than likely we're talking about a molecule. Okay, they make a note here that atoms can be the same or they can be different elements. Or if we have something that's made up of just one type of element, okay, that's going to be, or one type of atom, I should say, that's going to be an element. Okay, so some basic definitions for you, which you probably already know. Okay, so we're going to say in this class that science is empirical. And what does that mean? Well, it means that it's going to be based on observation and based on experimentation. Okay, so it doesn't really matter so much how you feel about something, more about how you can observe it and what kind of experiments you can do and what are the results of those experiments. Okay, so it's going to involve decision making and problem solving strategies. We're going to organize a plan of investigation. They say here it's fluid, meaning it changes over time. So if your first plan doesn't work, maybe you have to come up with a second plan. And there's no lockstep approach, meaning that you have to develop a strategy, and that strategy may change over time. Okay, so they make a note here that it says both a scientific and moral component, and we'll talk about that a little bit in the future. Just some terminology. Okay, so we have fact, scientific law, hypothesis, and theory. Okay, so let's break those down. This is a flowchart telling you kind of about the scientific method. I think this is best for you to kind of go over on your own if it helps you. I find this can be a little bit confusing for some students, so I usually just kind of skip over it. Okay, so fact. So a fact is a phenomenon which competent observers can agree. Okay, so that just means it's something that we all know. For instance, if I say that if I hold a pencil in the air, and usually I would demonstrate in this class with a marker or something like that, if I hold the marker in the air or a pencil in the air and I let it go, we would all say, okay, it's going to fall to the floor. And we'd all say that it did fall to the floor. Okay, so we're all competent observers, and we would all agree that the same thing would happen. Okay, so that's just a fact. Okay, so something we all can agree upon. So what about a law? Okay, so a law is a general hypothesis or statement about the relationships of natural quantities that has been tested over and over again and has not been contradicted. Okay, so this can also be written as a mathematical relationship. It is sometimes called a principle. Okay, so the biggest confusion you're probably going to have is what's a law and what's a theory. Okay, so a theory, also known as a principle, and the reason I bring that up is because you can kind of think about these as first principles. So for instance, if you know Newton's laws from physics, okay, so we also refer to those as being first principles. Okay, so those are laws. Okay, or we'll talk about a law in chemistry, law of conservation of matter. Okay, so that's a big one in chemistry, which just means that we don't create or destroy matter. Okay, so what we put into a reaction has to come out. So that's one of the big laws we use in chemistry. Okay, so it talks about natural quantities that have been tested over and over again and have not been contradicted. In other words, it's something that has just been shown over and over and hasn't been contradicted. So something like gravity, for instance. Okay, so Newton's law of gravity. Okay, so we'll compare that to a hypothesis. So a hypothesis, sometimes you may have, maybe your high school teacher or someone like that referred to this as an educated guess, and that's an okay way to say it. It's more like sort of a scientific question, more is a better kind of way to go about it. Okay, so a hypothesis is just a statement of what you think might happen. Okay, so it's almost like a question put into statement form. Okay, so it has to be falsifiable, meaning a hypothesis has to be able to be proven wrong. Okay, so if I say, if I use a prism with white light, I'll get a rainbow. That could be an example of a hypothesis. And if I do that and I don't get a rainbow, okay, then I've proven my hypothesis wrong. Or if I do get a rainbow, I've proven it correct. Okay, so that's what I mean by falsifiable. Okay, so it has to be testable. So I have to be able to construct some experiment that will allow me to test my hypothesis. As we say, in principle, it must be capable of being wrong. In other words, I have to be able to prove it wrong in order for it to be a good hypothesis. Okay, so an important idea here is that data never actually proves a hypothesis to be correct, it just supports it. Okay, so you gather lots and lots of data, and if it all points in the right direction, you'll say that your hypothesis is supported. We don't really prove them right or wrong. Okay, the next one, a theory. So again, theory and law are probably the toughest to get kind of straight in your mind. Okay, theory is an unifying explanation of a scientific phenomenon. And here they give us a definition: a synthesis of a large body of information that encompasses a well-tested hypothesis about certain aspects of the natural world. Okay, so a theory could be something as broad as something like the theory of relativity from Einstein. Okay, so a big broad topic that's very difficult to actually do any experiments on. Okay, so it's hard for us to travel at the speed of light, of course. Okay, so it's kind of hard for us to verify relativity, theory of relativity. Or it could be something more like what we use in chemistry, something like molecular orbital theory. Something that we can use to explain things that we observe. So for instance, something like why is liquid oxygen magnetic? Okay, so we can use molecular orbital theory, which tells us sort of how the electrons are stacked into the orbitals of an atom or of a molecule. Okay, so that's sort of like the example of a theory we'd use in chemistry. Okay, so it just kind of explains some phenomenon. So it kind of brings a lot together to explain a particular thing that's happening. So like my example, I say, okay, liquid oxygen is magnetic. Well, how can I prove that? Or how can I come up with a theory that suggests that that would be true. And again, a good theory is falsifiable. Okay, so it can be proven wrong based on the information I see. Okay, so just some basic definitions. Hopefully those were pretty much review for you. That's why I go over them kind of quickly. Those are things you've heard before. So what I like to do in class, since this is the first time having class with me, I like to do sort of immediate kind of test your knowledge kind of situations where I'll go over something and then give you a couple questions about it, or maybe even just one question about it, to test what you know. Okay, so see where you're going wrong and see what you're doing right. Okay, so with this, we'll just kind of go over this together. Some of them I'll actually have you pause the video. Okay, so you have the ability now to pause me talking, and you can work a problem out for as long as you need, and then you can resume the video, and you can I'll go over it with you, and you'll see if you got it right or wrong and where you went wrong, and hopefully those two things together will help you get it right in the future. Okay, so with kind of more simple ones like this, I'll probably just go over them with you together just in real time. Okay, whereas other ones, when I'm asking you to do calculations, I'll actually give you a chance to pause the video, and you can work it out real quick. Okay, so here we want to classify each statement as an observation, a law, or a theory. Okay, and there's a handful of these here. I think maybe there's 4 of them or so. Okay, so the first one, all matter is made of tiny indestructible particles called atoms. Okay, so we want to say if this is an observation, a law, or a theory. Okay, so based on what we just talked about. Okay, so take a second to think about it. Okay, so let's take a look at the answer. So this is going to be a theory. Why? Because it's describing something, okay, in a reasonable way. Okay, so it's sort of coming up with an idea that can explain something bigger than that. Okay, so it's saying that matter is made up of tiny indestructible particles called atoms. Why is that just a theory? Okay, so we can put all this information together that supports it, okay, but we really can never say for sure. That's kind of the best way I can explain it. Okay, the next one. So when iron rusts in a closed container, the mass of the container and its contents does not change. Okay, so I'll give you a second to think about this one. Okay, so this is going to be an observation. Why is it an observation? Because it's referring to something that I could measure. So it says when iron rusts in a closed container, the mass of the container does not change. Okay, so in other words, I can weigh it beforehand and I can weigh it afterward. Okay, so that would be an example of observation. It's something I can observe. Okay, the next one. Okay, it says in chemical reactions, matter is neither created nor destroyed. Okay, so this is going to be a law. So it's almost a statement of fact, right? It's sort of a statement of something that guides our ideas. These things are kind of abstract in certain ways, so if it seems like I'm struggling a little bit, it's because I am. They're difficult to explain, but hopefully you can understand them. So if it sounds like a first principle, if it sounds like one of Newton's laws or something like that, it's probably going to be a law. Okay, so yeah, matter is neither created nor destroyed. That's our first law of essentially, it's the law of conservation of mass. There's not really a name for it other than that. Okay. Okay, the fourth one, when a match burns, heat is evolved. Okay, so that's going to be an observation. Why? Because if I put my hand close to the match, I could feel that it was getting hot. Okay, so I can observe it. Therefore, it's an observation. Okay, so moving on, we're going to talk about the classifications of and properties of matter. Okay, so we're going to just talk about, firstly, what is matter? How do we define it? Okay, so matter is just anything that has mass and occupies space. In other words, it has volume. Okay, so it says it consists of atoms and molecules in motion. My favorite definition to give for matter is that matter is stuff. If it's a stuff, then it's matter. Okay, so matter is just anything that's stuff. Okay, so for instance, it could be graphite, it could be diamonds, it could be paper, it could be wood, a pencil, anything like that. That's all matter, or it's made up of matter at least. Okay, so it consists of atoms and molecules in motion. Okay, so what do we mean by that? So if we change the amount of motion that matter has, we actually change its state. Okay, so we're going to talk about three main phases. So when I say state, what I mean is the phase. Okay, so we're going to talk about three main phases in this class, and I know there is a fourth, which is plasma, of course. Okay, but really for this class, we're going to stick to these three. Okay, so we have solid, we have a liquid, and we have gas. Okay, so in our definitions, or really the true definitions here, we're going to say that solid is the most ordered type of matter, where on the other hand, gas is the least ordered, and liquid is going to be right in the middle. Okay, so here we have three examples of that. So we have some sort of solid green cube. Okay, so that's going to be our solid matter. And maybe if we warm that up a little bit, it becomes liquid matter, and you can see that we go from nice, highly ordered little columns and rows of atoms, okay, to sort of a more disordered, just sort of blob of atoms, and then into a gas, which is just sort of random atoms, I should say. Okay, so let's talk about each state of matter in a little more detail. So the first one we'll talk about is solids. Okay, so a solid has a rigid shape and a fixed volume. Okay, the external shape can reflect the atomic and the molecular arrangement. So the arrangement of atoms or molecules in a solid can either be crystalline or amorphous, and we'll talk about what each of those are. Okay, so we say it has a rigid shape and a fixed volume. Okay, so in order to change the shape of a solid, or the volume of a solid, we essentially have to break bonds. Okay, so if it was, for instance, a diamond, we'd have to cut it in some way. Or if it was, I give the example here, cotton candy, just because it's an easy one to sort of remember, so you have to pull it and sort of break those strands of sugar. Okay, so we say that the external shape can reflect the atomic and molecular arrangement. What do I mean by that? Okay, so what I mean by that is the external appearance, okay, so the external shape is going to have a lot to do with how the molecules are arranged. And in this class, we're going to talk about two main arrangements. So we're either going to have crystalline or amorphous. So amorphous solid, or an amorphous solid, is going to be a highly ordered type of solid. So remember that solids are already our most highly ordered form of matter. And on top of that, if we have a crystalline solid, it's going to be even more highly ordered. So these are going to be things like your gemstones. Okay, so I give the example here of diamond. And the reason I like to give the example of diamond is because, believe it or not, diamond is just made up of carbon. That's all it actually is. It's an extremely pure and ordered form of carbon. So there's actually no difference between a diamond that you might have in a ring or something like that, or a piece of jewelry. Okay, there's no difference between that and the pencil that you probably are taking notes with right now. Okay, so the only difference between those two forms of matter, so they're both solids, the only difference between those forms of matter is that diamond is a crystalline solid, whereas the graphite in your pencil, also made of carbon, is more like an amorphous solid. So it just has a random arrangement. Okay, so if you notice closely here in the crystalline solid, we have 1, 2, 3, 4, 5, 6 atoms in a nice little ring. If we were to look at the next one, okay, and just over and over and over again, you'll see that arrangement. Okay, so it's a repeating pattern, in other words. Okay, and when you get up to some of the things like inorganic chemistry, we have names for these patterns. We don't have to worry about that right now. Okay, but the difference between a crystalline solid and an amorphous solid is that pattern. Okay, it's that symmetry, that ordered. Okay, so these are highly ordered forms of matter. So this would be like a gemstone, or again like a diamond. Okay, so highly ordered form of matter, or a highly ordered solid, I should say. So we have that repeating unit over and over and over. That's going to be a crystalline solid. Or if it's disordered, where we just have the atoms sort of in a random, just sort of solid, just sort of smashed together, that's going to be amorphous. So there's it's ordered because it's still a solid compared to like a liquid or a gas, but compared to a crystalline solid, it has almost no order to it. Okay, and again, I give the example cotton candy, just as an easy way to kind of remember it. Okay, the next one, liquids. Okay, so that we say that liquids have a volume, so a fixed volume, but no fixed shape. So they're generally speaking going to take on the shape of their container. And we say that they're fluid, meaning that we can pour them. Okay, so we're pretty familiar with liquids. So this is our sort of middle state of matter. Okay, so it just has sort of random order in terms of how the molecules are arranged, but they're still close enough connected with each other that they're going to have a fixed volume. So they're not going to sort of just separate from each other randomly. Okay, so some examples of liquid might be a glass of water. And I have some examples here. So milk, oil, coffee or tea, soap, water, maybe some sort of juice. Okay, so we're familiar with liquids, and these are found throughout our daily lives as well as solids. Okay, next one, gas. Okay, so important thing to remember with liquids before I forget here, they have a fixed volume but no fixed shape. So they're just going to take on the shape of their container. Okay, so whether it's in a bottle like for dish soap or a glass like for water, it's just going to take on that shape, and you could pour it into that container. Okay, gases. So gases do not have a defined volume or defined shape. So the volume is going to be defined by the container, and it's going to expand to fill that container. Okay, and that container can be the size of your room that you're sitting in, or it could even be as big as the globe. Okay, so we don't really think about this as we walk around, but we're actually walking around in just a sea of gases. Okay, and they've expanded to fill the size of the ozone, essentially. Okay, or you could think of releasing a gas into a room. Okay, it's going to fill the room, if it's, to some degree. Okay, or you could think of it in terms of filling a balloon. Okay, so you blow up a balloon. Okay, so the gas is going to push out against the balloon, and it's going to be limited in volume and shape by the shape of that balloon and the volume of the balloon. Okay, so just some examples. Could be a balloon that you fill with either helium or just your breath. It could be a halogen gas, which is what's used in neon lights. Okay, so I don't know, just kind of an interesting fact here to help you remember that neon lights are actually just the different noble gases, and depending on which one you use will change the actual color. So they're all named after neon. We call them neon lights. But if you want to change the color, you can change the mixture of gases inside. Okay, so that's another example of a gas. My third example here would just be water vapor. So all of this coming off of this water. Okay, so we're going from liquid water to gaseous water. Okay, so they have no fixed volume, no fixed shape. They're going to expand to fill the volume and the shape of their container. Okay, their movement is unrestricted. So if you look a little bit closer at these, so this is a couple slides I actually stole from my 1412 class, but I think they're good. I think they apply here as well. Okay, so we go from a gas on the left all the way to solid ice on the right. Okay, so we're just talking about water in this case. So each of these red spheres represents an oxygen. Each of the white spheres represents a hydrogen. Okay, so we're going to go from gas to solid. Okay, so in a gas, what we call steam when we're talking about water, the particles are far apart. In other words, there's a lot of empty space. So one thing to remember is that gases are mostly made of empty space. Okay, the particles have complete freedom of motion. So notice the huge gaps between water molecules. Okay, so this would be like gaseous water. Notice the huge spaces. Okay, notice that they don't really have any certain orientation according to each other. Okay, so they have complete freedom of movement. They're made up of a lot of empty space, and it has complete disorder. Okay, and by complete disorder, I mean that they're free to move around however they like. So one gas molecule is not restricting the movement of a second gas molecule. Okay, so that's gases. So that's our least ordered form of matter. Moving to a liquid, we have particles that are close together. They form clusters, and they're free to move around each other. Okay, but they still have some restriction, so there's still some interaction between water molecules, And there is a level of disorder. So not as much as a gas, okay, but we still have a level of disorder. Next one, we have solid, which would be, in this case, ice if it's water. Okay, so in this case we have particles that are close together, and we have particles that are essentially in fixed positions, and it's highly ordered. Why do I say essentially in fixed positions? Well, that's because matter is always in motion, unless we're at absolute zero. So even though something appears solid, we know that the atoms and the molecules are actually still vibrating, albeit slowly, and albeit very minutely, perhaps. Okay, but there's still motion there. Okay, so what I want to point out here before we move on, though, is that if we have liquid, so we have atoms or molecules that are close together. So they're still interacting. So they're free to move relative to each other, but in order to get too far apart, they have to start to break apart. They have to start to break an attraction to each other. Okay, but they're still free to move around, whereas in a gas, they're free to move around however they like. Okay, so comparing that to a solid, now we have highly ordered matter, and it's restricted in its movement. In other words, this oxygen or this hydrogen is going to want to point here, this is going to want to point here, and they're not going to move around. Okay, and if you were to look very closely at this, you would see that they're all sort of facing an oxygen, and the oxygens are all facing a hydrogen. Okay, we'll get into that later, but you understand that they're highly ordered, and the relationship between each other is very strong. Okay, so they have a high interaction, whereas liquids we have sort of a medium interaction, with a gas we have no interaction. Okay, and the liquid and the solid phases we'll call the condensed phase, or condensed phases. Okay, just meaning that we've condensed a gas into a liquid or a solid. Okay, so just to sort of reiterate some of the things I said before. So a gas has indefinite shape, indefinite volume. In other words, it has no fixed volume or shape. Okay, so it's just going to take on the shape and the volume of its container. It's compressible. So since we have all this empty space, we could actually shrink that down if we wanted to. Okay, so something like a compressed gas cylinder. So this could be something like the helium tank when you go to get a balloon filled. Okay, so that's an example of a compressed gas. So the reason it's so ready to come out of that container, it's because it has been so highly compressed. Those cylinders that you might see at the grocery store or something, those contain, I think, about 3,000 or 5,000 psi. Okay, so very, very lots and lots of pressure, and that's because we can compress that empty space down so much. Okay, they have low density, so if it's not a compressed gas, it's going to have low density. Why low density? Because it's mostly empty space. And of course, we know a gas can flow. Okay, so we can so much as push a gas through a gas line, or if it's a heavy gas, we could even pour it maybe. Okay. Moving to a liquid, we know a liquid has indefinite shape, but it has a fixed volume. In other words, it's going to take on the shape of its container, but the volume won't change. It's not very compressible. We're going to say it's not compressible for just terms of argument. Okay, so we can't really mush that empty space in. Has high density, and it will flow. So we know that we can pour liquids. And since they're not really made up of empty space like a gas, we're going to say they're not compressible. And then they have high density. Okay, so the next one, solid ice. Okay, this has a fixed shape and fixed volume. The only way to change the shape or the volume is either to change the state of matter and then solidify it, or to actually break it. Okay, it has high density, and we know that we can't pour solids. Okay, so they don't flow. So gases and liquids will flow. Gases have low density. Liquids will flow, but they have high density. Solids won't flow, but they have high density. Okay, so we're going to break down our types of matter into a couple different categories. So we're going to break these down into either pure substances or mixtures. Okay, and that's going to be based on their composition. Okay, so if we look at this chart, okay, we're going to go all the way from just general matter all the way down to the type of matter. Okay, so starting from matter, we'll say, is it a pure substance? In other words, is it made of only one type of matter, or is it made up of several types of matters? Oh, I'm sorry. So our first question here is going to be, does it have variable composition? In other words, is it going to be, I kind of said it right, but kind of backwards too. So our first question was variable composition. So is it made up of more than one thing or only one type of thing. Okay, so if it's not variable, in other words, if it's something isn't variable, it would be made up of only one type of matter. Okay, if no, then we're going to call that a pure substance. So if it's only made up of one type of matter, that can be either molecules or it could be atoms, that's going to be no, meaning that it's a pure substance. Okay, the next question is, can we separate it into simpler substances? If we can't break a pure substance into anything more simple, that's going to be an element. If we can break it into more simple substances, that's going to be a compound. So an example of an element is helium. Okay, so if it's the way that you find it on the periodic table, for instance helium, that's going to be an element, so it's going to be a pure substance, and it's going to be an element. If it's not the way you find it on the periodic table, for instance water, so even though it's made up of only hydrogen and oxygen, okay, so all water is made up of hydrogen and oxygen, so it's the same molecule over and over, but I could break it down into smaller substances, so that's going to be a compound. Going back to our first question, if it is variable composition, meaning if it does have more than one thing in it, okay, that's going to be a mixture. And then we can break those down into either heterogeneous or homogeneous. Heterogeneous just meaning it has different things in it, or it's in different phases, you could say. That's probably the better way to think of it. Homogeneous just meaning that it's all in the same phase. So an example here of a heterogeneous mixture would be something like a beach or a glass of sand and water put together, or a mixture of sand and water. The important thing here is you can actually define the difference between the sand and the water. Okay? So that would be a heterogeneous mixture, meaning they're in different phases. Okay, so I could draw a line here. If I was to ask you, show me where the sand is and show me where the water is, you could easily show me. Okay, whereas if in a homogeneous mixture, so for instance, here we have tea with sugar, so we have water molecules, we have the oils from the tea, and then we also have sugar molecules. So if I was just to hand you a glass of tea and ask you to point to the sugar and ask you to point to the tea molecules and the water molecules, you would be pointing all at the same thing. Okay, so you wouldn't be able to physically look and see what was what. Okay, so you wouldn't be able to see what was the tea, what was the water, what was the sugar. Okay, so sort of to explain that a little bit easier. I know this flowcharts get a little bit weird. Okay, so a mixture can be composed of two or more different types of substance. Okay, and we either have a pure substance. Okay, so this could be molecules or elements. Okay, so an example would be a saline solution. It's made up of table salt or sodium chloride and water. Okay, so what they're trying to say here is that we could have a mixture made up of two pure substances. So the example they're giving here would be a saline solution made up of pure table salt and pure water. So those are two pure substances coming together to make a mixture. I think the phrasing there is a little bit confusing, so hopefully that clears that up. Okay, and it says the composition of the mixture can be in varying proportions, and that's true. So we could have a lot of water and a little bit of salt, or we could have a lot of salt and a little bit of water. Okay, so that would be example of a mixture. And these come in two types, so we discussed this a little bit before. Okay, so two types of mixtures would be homogeneous, meaning that the composition is the same throughout the sample. In other words, like with the glass of tea, you can't point to what's the tea and what's the sugar and what's the water. Or it could be heterogeneous, where the composition varies throughout the sample. So again, the best example of this is sand and water together. So you could shake the mixture up really hard and let it settle, and you'd easily be able to point to, okay, that's the sand and that's the water. And they also give the example here of the forest floor. So meaning that it's just a mixture of dirt and leaves and sticks and all kinds of stuff together, bugs, all that kind of stuff together. Okay, so if you can't determine what's in what phase, in other words, you can't point to, okay, that's the sand, that's the water. I can't point to, that's the tea molecule, that's the water molecule. That's going to be homogeneous. But if it's heterogeneous, it means I can point to the different phases. So I can say, okay, that's clearly the solid phase, and that's clearly the liquid phase, or however it is. And you could do that without even knowing what the substances are. Okay, and we'll look at that in just a second. Okay, we can break this. Well, in the next little section here, we'll talk about atoms and elements. So atoms are going to be the smallest unit of an element that has the chemical properties of that element. Okay, so an atom consists of a nucleus, which is composed of protons and neutrons and electrons that occupy the space around the nucleus. Okay, so sort of a definition we already know here, but just to kind of put it in formal definition here. Okay, so, and just remember that in a neutral atom, we have the same number of protons as electrons. Okay, so how is an atom different than an element? So they're composed of the atoms that have the same number of protons. Okay, so the element carbon is made up of atoms that have 6 protons. Okay, they're pure substances, and the individual atom of an element may differ in mass due to the varying numbers of neutrons present in the nucleus. In other words, here we're talking about isotopes. We'll get to that later. Okay, so what's the difference here? So really we're kind of saying the same thing. The big difference here is that an atom, okay, so an atom is just made up of nucleus and electrons. Okay, so it's just the smallest unit of an element that retains the chemical properties. And the reason we draw this definition is because some elements, we have like diatomic elements, for instance. Okay, so we draw this definition because something like lithium, for instance, is just one lithium atom. Okay, so in its elemental form, it's just one lithium atom. Okay, whereas if we have something like chlorine, for instance, we have a diatomic element. Okay, so we have Cl2, which you'll see a lot, chlorine gas. Okay, so it's a sort of a square rectangle situation where all rectangles are square, but not all squares are rectangles. Okay, so it's one of those situations. Okay, the important thing is to just remember that atoms are just the smallest unit that retains the properties. So, for instance, I could break a sample of something down into atoms, and that would be the smallest I could go without losing the properties of the element. Okay, whereas if I have a sample of a pure element, it's going to be considered a pure substance, and it's essentially going to be the way that it appears on the periodic table. So if you can find it on the periodic table, essentially you're talking about an element. Okay, so not that complicated of definitions, but they sort of sound complicated, but it's really not. Okay, so if you can find it on the periodic table, it's an element, but just remember the smallest unit of something that still has those properties is called an atom. Okay, molecules and compounds. Okay, so a molecule is the smallest unit of a compound that retains the characteristics of the compound. So again, this is very similar to the atoms and elements. Okay, so a molecule is just an individual piece of a compound. Okay, so if, for instance, if I was to take a sample of water, if I pull one H2O out, I would be pulling one molecule out of that compound. Okay, so where the compound would be the whole sample of water, and the individual H2O would be just one molecule. Okay? And these two terms are sort of used interchangeably, to be honest with you. Okay, but generally speaking, molecules are compounds that are a combination of two or more elements and definite ratios by mass. Okay, so the character of each element is lost when forming a compound. We know that chemical compounds are composed of two or more elements, and they can be the same or that they can be different. Okay, the composition of molecules is given by the molecular formula. So example, a water molecule, as I've said a few times now, is just H2O. Okay, so that's just the molecular formula. Okay, so sort of the takeaway here is that when we come back up to this idea of definite ratios by mass, in other words, if we have 2 hydrogen and 1 oxygen, then we have 1 molecule of water. If we don't have that, we have something else. Okay, so a compound is just a combination of 2 or more elements and some ratio. Okay, and that particular ratio may have a name or it may have a particular formula, such as water. We know it's just H2O. If we have 2 H's and 1 O, okay, we have water. Okay, and we'll come back to this idea when we get to Dalton's laws. Okay, and I'm sorry if I'm moving a little bit fast with this, but a lot of this we're going to come back to. Okay, so this is just sort of a jog your memory kind of chapter. Okay, so here we're going to classify each substance as a pure substance or a mixture, clarify if it's an element or a compound, and if it's homogeneous or heterogeneous. Okay, again, so we'll just kind of walk through these together. Okay, so the first one we'll do, and feel free to pause the video if you need to, okay, if you want to come up with these answers, but I'm just going to kind of read the question and I'll pause for a second, and then we'll go over the answer. Okay, that's just the way I would do it in class, so that's the way we'll do it here. Okay, so we want to classify each substance as a pure substance or a mixture, clarify if it's an element or a compound, and if it's homogeneous or heterogeneous. So the first one is sweat. Okay, so the first one we want to say is, it is a pure substance or a mixture. So sweat, pure substance or a mixture. Okay, so sweat's going to be a mixture. Why? Because we have water, we have toxins that come out of our body, we have salts, we have all kinds of stuff that comes out in sweat. Okay, so it's going to be made up of more than one thing. Okay, so that would be a mixture. And is it heterogeneous or homogeneous? Well, it comes out as just sort of a dissolved liquid, right? With liquid with salts dissolved in it. So that would be homogeneous. Until, of course, maybe the water evaporates, then it would be heterogeneous. Okay, the next one. Carbon dioxide. Okay, so first, is it a pure substance or a mixture? Okay, so this one's going to be a pure substance. Why? Because it's only made up of one type of molecule. Okay, so if we have carbon and we have oxygen coming together to form carbon dioxide, but our entire sample of carbon dioxide is only made up of carbon dioxide. Okay, the next one, is it homogeneous or heterogeneous? Okay, it's going to be, oh sorry, it also wants to say element or a compound. Okay, so this is going to be a compound. Why? Because it's made up of two or more elements. Okay, so we have carbon and we have oxygen coming together to form carbon dioxide. So it's going to be a compound. I always forget on this question that one's going to be element or a compound. I do that in class too all the time. Okay. Okay, the next one, aluminum. Okay, so is aluminum going to be pure substance or a mixture? I think I kind of gave this one away already, but that's going to be a pure substance. Okay, so since it's not a mixture, we want to know if it's an element or a compound. Okay, the answer to this one's going to be element. Why? Because we can look in our periodic table and we can see that we have aluminum. Okay, so we know it's going to be an element. Next one, vegetable soup. Is it mixture or a pure substance? Okay, this one's going to be a mixture. Why? Because when we make vegetable soup, we put in, what do we put in? We put in green beans, carrots, all that kind of stuff, and then we put in our beef broth and some water, and we cook it together. Okay, so it's going to be a mixture. Next part, since it's a mixture, is it homogeneous or heterogeneous? Okay, so this one's going to be heterogeneous. Why? Because if I was to take a bowl of vegetable soup, I could point out, okay, there's the green beans, there's the carrots, that's the broth part. Okay, so you could pick out each individual piece of it. Okay, so that would make it heterogeneous. Okay, so I'll give you a second with all those answers up there in case you need to pause it and go back over these. Okay, so now we're going to do the same thing, okay, but we're going to do this with sort of graphically instead of just with words. Okay, so try to go through each one of these, classify it as pure substance or a mixture, and then clarify if it's an element or a compound. And if it's a mixture, say if it's homogeneous or heterogeneous. So this is a situation where I would like you to pause this and try to answer each one of these, and then we'll come back and go over it. So I'll give you a second to do that. Okay, so the first one, I see that I have sort of a repeating molecule. Okay, so I have red, black, red. Okay, and I know that this is carbon, oxygen, and oxygen. Okay, so these are all just CO2 molecules. Okay, so is this going to be a pure substance or a mixture? Okay, so since we have just one type of molecule repeating, that's going to be a pure substance. Okay, now is it going to be an element or a compound? Okay, well I just said we have carbon and we have oxygen put together. So it's not going to be an element, so it has to be a compound. Okay, so we have two or more types of elements coming together. The next one, we want to know, is it a pure substance or a mixture? Okay, so here I see that I have some sort of chain type molecule, then I have a water molecule. Okay, so I have two different things here. So is that going to be pure substance or a mixture? And of course that has to be a mixture. So we want to say, is it homogeneous or heterogeneous? And remember, I told you if it's heterogeneous, you can draw a clear distinction between one layer and the other, or one form of matter and the other. Okay, so here I can draw a clear barrier between the water and whatever's floating on top of it. So it would be homogeneous or heterogeneous. That's going to be heterogeneous because I can clearly see which is which. And this was an example of something like oil on top of water. So oil exists as these sort of long carbon chains like this. Okay, so we know that oil and water don't mix together, so that would be a heterogeneous mixture. The next one. Okay, so this is a pure substance or a mixture. So I take a closer look at this. I see I have water molecules. I'm just sort of drawing these triangles, okay, for water molecules, just showing that they're the same. Okay, then if I look down below that, I see again some carbon, some oxygen, maybe I have an alcohol here. I see that again, and I see that again. Okay, so is this a pure substance or a mixture? So I have one or more compound coming together, or I have two or more compounds coming together. So I know that this is going to be a mixture. Okay, the next part, do I want to know if this is homogeneous and heterogeneous? And this part might not be so easy, doing this graphically, but what you want to do is you want to ask yourself, can I define a clear separation between one and the other? And the answer would be no. Okay, so we just have this alcohol interdispersed between water molecules. Okay, so that would be homogeneous. Okay, and the last one here, I just have sort of white spheres. So maybe this is some kind of gas or something like that. So it's just going to be a pure substance or a mixture. I just have one unit repeating. Okay, so that's going to be a pure substance. Is it going to be an element or a compound? Okay, so I just have a singular atom sort of floating by itself. Okay, so that's going to be an element. I'll give you a second with all of these on the same page. Okay, so in this next section, we're going to talk about physical and chemical properties as well as physical and chemical changes. And we're going to define what is a physical property, what is a chemical property, what's a physical change, and what's a chemical change. Okay, so the first thing we're going to talk about is a physical change. Okay, so when a physical change occurs, a substance does not change into a new substance. Okay, so the easiest example of this would be ice changing into water and water changing into steam. Okay, so I have a little graphic here that just shows us water. If we were to cool it down, we can turn into ice. In other words, we can turn liquid water into solid water. So the important thing here is that this is a sample of H2O, liquid H2O. This is also a sample of H2O, just solid H2O. Okay, and if we were to take that same sample of water, or to apply heat instead, it would turn into steam. In other words, gaseous water. Okay, still H2O. The only thing that's changed here is that this is a solid, this is a pure liquid, and this is a gas. Okay, so we've changed the state of matter, but we haven't actually changed anything about that matter in terms of its chemical composition. Okay, so we haven't changed it into a new substance, we've just changed its physical state. Okay, so if all we change is its physical state, then all we've done is we've gone through a physical change. So we haven't combusted it, we haven't changed its chemical composition in any way. Okay, it's just a physical change. Okay, and so some physical properties. Okay, so physical properties are going to be those you can measure without changing the substance. Okay, so for instance, we can measure the density of something. So density is actually a derived unit, but we can measure the mass of something and the volume of something without having to break it down. In other words, I don't have to react water with something to get the mass of a sample of water. I don't have to combust water to get its volume, which combusting water would be very difficult, but I don't have to do that. I can just measure the volume I can measure the mass with a scale or a balance. And I can measure the volume with a beaker or with a graduated cylinder, anything like that. Okay, from there I can take the mass or the volume and get density. Okay, the color or the color intensity. So I don't have to look at something and change it chemically to say, okay, that's orange or that's blue. All I have to do is look at it. So I haven't had to break it down physically or chemically in any way. Okay, the particle size, melting or the freezing point. So I can heat something up and measure its melting point, or I can cool something down and measure its freezing point. Okay, the boiling point, I can take water and boil it and measure the temperature, and all I'm doing there is just changing from liquid to steam. And the texture, so we could touch something and say it's smooth or it's rough or what have you. Okay, so those are all examples of physical properties. Okay, so the important thing here is that if I'm going through a change and that change does not break down a substance chemically, then that's a physical change. And if it's something I can measure without altering a substance chemically, that's going to be a physical property. Okay, so just sort of to reiterate that. Okay, so here we have a sample of liquid water, and we're heating it. So maybe we're heating it on the stove. Okay, in other words, we're boiling it. So we've made liquid water go from liquid to gas. Okay, so now we've gone from liquid water to gaseous water. But notice, so here we have H2O, and here we still have H2O. So we haven't changed it chemically in any way. We still have just water, just H2O. So we haven't broken any chemical bonds, we haven't made any new chemical bonds, therefore it's just going through a physical change. Okay, so what about a chemical change or a chemical property? So a chemical change is something that occurs when we form a new compound. So we take one type of matter and we go through some chemical reaction to get a new type of matter. Okay, so in other words, it's going through some sort of a transformation. Okay, so an example of a chemical change might be just rust. So if we have an iron nail and we leave it outside and it rains for a few months or a few days or a few weeks, whatever it is. Okay, so we can go from just a nice iron nail. Okay, so maybe go from a pure iron nail, and then the rust that forms on the surface, now we're going from, so just this pure sort of cubic iron structure. Well, now we've inserted oxygen. So notice we have just iron, so just iron molecules connected. Well, now notice we've actually changed the structure, so now we've added in oxygen. So now we have iron and we have oxygen. Okay, so in this top one, so sort of get rid of some of that mess there, we just have iron molecules or iron atoms. Okay, so here we have iron atoms and oxygen atoms. So we've actually changed the chemical composition of the matter. Okay, so therefore we've gone through a chemical change. Okay, so we've gone from one type of matter to the other. In other words, what we put into a reaction, what we put into this reaction is different than what we got out of it. So we've gone through some chemical reaction or some chemical change. Okay, and just before I forget, so if we have a chemical property just means you have to change the chemical composition in order to measure that property. Okay, I think we'll have some more examples of that in a moment. Okay, so for instance here, okay, so we have some examples of both chemical and physical changes. Okay, so the first one, here we have dry ice. So dry ice is just solid carbon dioxide. Okay, so if we were to take solid carbon dioxide and leave it in a room, or maybe put it into a cooler and go on a trip with it or something like that. I don't know what you're doing. Okay, so we take solid CO2 and we would just place it on a table, for instance. That solid CO2 is going to go through sublimation. So it's going to go from solid CO2 to gaseous CO2. So the important thing here is notice we're going from nice ordered CO2 to gaseous CO2 with very little order. The important thing here is that we haven't changed the molecule in any way. So the only thing we've changed is the physical state. So we've gone from solid to a gas. Okay, so since we haven't changed it chemically, this is going to be an example of a physical change. Sorry, I sort of wrote over the thing I was trying to circle there. Okay, that would be a physical change. So I haven't changed the composition, I've just changed the state. Okay, what about sugar? So we're going to dissolve sugar into water, maybe. Yes, maybe we're making some tea or something like that. Okay, so we're going to take solid sugar, we're going to add it to the water, and what are we going to get out? We're going to get out aqueous sugar. Okay, so we haven't, again, we're starting from C12H22O11. Okay, we're getting back out C12H22O11. So we haven't altered the chemical composition in any way. All we've done is dissolve it. We've made it go from a solid state to an aqueous state, which just means it's dissolved in water. Okay, so we haven't changed it in any chemical way, therefore that's also a physical change. Okay, the last one here. Okay, so here we have propane. So we have just a little propane burner, or a propane torch maybe. Okay, so call it a propane gas burner here. Okay, so here we're taking propane, C3H8, which is in the gaseous state. Okay, so it's condensed inside of the little bottle. We turn the valve, release it, and we ignite it. Okay, so we take gaseous propane, we combine it with oxygen, and just like any chemical combustion, we're going to get out CO2 and water. Okay, so notice we put in propane and we put in oxygen, but we got out CO2 and we got out water. In other words, we've chemically changed the propane. So what comes out of this reaction is not the same as what we put in. So we put in propane, but we got out CO2 and water. Okay, so we're actually changing the chemical composition, so therefore this would be an example of a chemical change. Okay, so just based on what we just talked about, I'm going to go through a list of several properties of isopropyl alcohol, and we just want to classify them as physical or chemical. Okay, so I'll give you a second here. You can pause the video and go through and try to categorize these as either physical or chemical. Okay, and you should be able to do this pretty much based on what we talked about. Okay, so when you come back, we'll go over them together. Okay, so let's take a look at each one of these and just decide whether they're a chemical or they're a physical property. So the first one, we say that something is colorless. Okay, so that's going to be a physical property. Why? Because all I have to do is just look at it and I can see that that's colorless. I don't have to even really touch it or do any experiments necessarily. Okay, just to see that something's colorless. Okay, the next one, we say that it's flammable. Okay, so how would I know whether something is flammable or not? Well, I would have to take the sample and I would have to actually combust it, right? So I have to go through some chemical change, so that would be a chemical property. So it's a liquid at room temperature. So how could I observe this? So I could just take a sample of isopropanol, let it sit at room temperature, and observe what state it was in. Okay, so I don't actually have to do anything to it, therefore it's physical. Okay, so I could measure the temperature if I wanted to, but that doesn't change the composition of the matter. Okay, the next one, the density is 0.79 grams per milliliter. Okay, so again, I talked to you before about saying that we could take the mass of a sample, take the volume of sample, without having to alter it chemically in any way. Okay, so this is going to be a physical property. Next one, mixes with water. This one's a little bit tricky. Okay, so that's actually going to be a physical property. Okay, so again, it's just going to mix with water. We didn't say it reacts with water. Okay, that would be something different. But just saying that it mixes with water, that's just a physical property. Okay, so sort of similar situation here. Okay, so determine whether the following changes are chemical or physical changes. And again, I'll give you a second to pause, go through these, and we'll talk about them together. Okay, so let's take a look at each one of these. So the first one. So remember, we're trying to decide whether these are physical changes or chemical changes. So the first one, drying your hair. So you take a hair dryer, or you just let it air dry, however you do it. Okay, you just let your hair dry. So what are we doing? We're just making the water go from what? A liquid water stuck to our hair, and we're just driving it off into gaseous water to leave our hair dry. So is that a physical or is that a chemical change? Okay, that's going to be a physical. Dyeing your hair. I'm sorry. I read that as drying, not dyeing. Okay, so dyeing your hair, excuse me. So you're actually going to add some color to your hair. Okay, well in that case, we actually are changing the chemical composition of our hair. Okay, so we're taking some chemical and we're sort of interweaving it with our hair molecules. Okay, so that's going to be a chemical change. Squeezing oranges. Okay, so we take some oranges and we're going to juice them or squeeze them, let the juice come out. Okay, so is that going to be chemical or physical? Yeah, it's going to be physical, right? So all we've done is change it from being inside of the orange to the outside of the orange. We haven't actually changed anything about it. Okay, the next one, spoiling food, chemical or physical. This is going to be chemical, since we have an actual chemical reaction going on. So we have microbes going in and eating the surface of the food and changing it to something else. Okay, so we have maybe it's sugar molecules turning into waste molecules. Okay, so that's actually a chemical change. The next one, exploding fireworks. Okay, now those you could even say this as combustion. Okay, so that's going to be chemical. Okay, so we're actually taking something and burning it. Next one, mowing a lawn, chemical or physical. Okay, so we're just taking long grass and making it short grass, so just cutting it in two. So that's just going to be physical. So we haven't actually changed it in any way. Okay, the next one, dew forming on grass. Okay, so what's this actually happening? So we have gaseous water turning into liquid water. Okay, so we're just changing physical states. So those are going to be physical changes. Okay, I'll give you a second with those on the screen. This next one will be sort of similar to how we did this before. So here we have sort of pictorial representations of what we just talked about. Okay, so again, go through each one of these, and you want to know whether it's a physical or a chemical change. Okay, so in the first one, part A here, so we have some butane molecules inside of a lighter. Okay, so the first one here, all we do is we push the button. So we don't actually flick the flint and steel. Okay, so all that's happening is now the gas or the liquid inside is turning into gas. So the liquid butane is turning into gaseous butane. So would that be a physical or a chemical change? Okay, well, since we're not actually combusting it, that's going to be a physical change. The next one, so now we've pushed the button, and we've also sort of lit the lighter, right? So we flicked the flint and steel, so we've actually started to combust the butane. Okay, so we've gone from liquid butane to gaseous butane, and now we've actually combusted that butane. So that'd be chemical or physical. That's going to be chemical, right? Since we're actually combusting it. Okay, and then the last one, we have just sort of a bowl of water or pan of water on the stove. We're heating it up, so we're making that liquid water turn into gaseous water. So is that going to be physical or chemical? And of course that's going to be physical, since we haven't actually changed the matter in any way. Okay, so we're going to move away from sort of this chemical and physical property discussion. Hopefully you got those down. Just remember that if you change it chemically, then it's a chemical change. If you don't change it chemically, then it's a physical change. Okay, so the next part will sort of be hopefully a refresher about a little bit of thermodynamics, or maybe sort of a brief introduction, which we'll get into more at a later time. Okay, so first of all, we're going to say that energy is the capacity to do work. Okay, so it's a fundamental part of physical and chemical changes of matter. Okay, so in order for a physical change or a chemical change to take place, we have to have some energy, either in the form of heat energy or in the form of chemical energy. Okay, so we're going to define work as the action of a force applied across the distance. Okay, so a force can be either a push or a pull. We can also have electrostatic force. Okay, so this has to do with pushing and pulling with electrical charge. Okay, so the important thing here is to know that energy of the universe must be conserved. Okay, so this is our first law of thermodynamics. So remember, we talked about laws versus theories versus hypothesis. Okay, so this is an example of a law. Okay, so the energy of the universe is conserved. So in other words, so we have this little balance here. So the energy before has to be equal to the energy after. So no matter what. So it has to go somewhere. And we talk about this in thermodynamics as it being going from the system into the universe, or into the system, so from the surroundings into the system, or from the system into the surroundings. Okay? And all of those are inside of the universe. Okay, so the energy inside of the universe has to be conserved. Okay, so that's your first law of thermo. So we can classify energy as two types. So we either have kinetic or potential. Okay, kinetic energy is associated with movement, whereas potential energy will be associated with storage. Okay, so if we have sort of an object in motion, so we have 1/2 mass times velocity, so we have some body in motion, okay, then we have kinetic energy. Okay, if on the other hand we have maybe a boulder very high up on a hill, okay, we have the mass times the height times the gravity, that gives us our potential energy. The more important thing here is just to remember that kinetic energy is associated with movement, where potential energy is associated with storage. Okay, we can convert from one type of energy to the other. So I have a little wind-up flashlight here, which is an example of turning mechanical energy, so turning your arm, into chemical energy, or in other words, sort of electrical energy. Okay, so that's just a transformation of energy occurring there. Okay, we see here when matter undergoes a chemical or physical change, the amount of energy in the matter changes as well. Okay, so changes in the matter, both physical and chemical, results in the matter either gaining or releasing energy. So it could be that we're heating the matter up, we're putting energy in, or maybe we're cooling it down, which we would be taking energy out. Okay, or it's going through some chemical transformation where we have a lot of stored potential energy, chemical energy, and we're releasing that by forming a new bond, or we're breaking a bond, or we're putting energy in, something like that. Okay, so whenever we go through these changes, physical or chemical, we're changing the amount of energy stored in the inside of the matter. Okay, so just talking a little bit about units here. Again, this chapter sort of jumps a little bit. Okay, so from kind of one topic to the next, and we're going to get more and more in detail as we go on. This first chapter is really just sort of an introduction. So if it feels like we're jumping topics, that's basically what we are a little bit. Okay, so just bear with me. We're going to set some things up, but all this is going to be useful for you continuing on. Okay, so all measurements consist of two parts. So we have the scalar, or in other words, the unit. Okay, so this is like meters or kilograms. So I have 5.9 what? Well, I have 5.9 meters. Okay, versus maybe I have 5.9 centimeters. Okay, so those are very different. So the unit tells me how big of a thing I'm talking about. Or here, maybe I have 3.7 kilograms or 3.7 pounds. Okay, so that tells me how much, or the number tells me how much, the unit tells me of what. Okay, so I have 3.7 what? Well, I have 3.7 kilograms. Okay, the numerical part tells me how many of that unit I have. Okay, so for example, I sort of similar situation here. So I have 25 what? I have 25 centimeters. Or how many centimeters do I have? I have 25 of them. How many feet do I have? I have 1. Okay, so the scalar tells me how big of something we're talking about. The numerical part tells me how many of those. Okay, the numerical values are going to reflect the precision of the instrument used to make the measurement, or the type of data and measurements collected. Okay, so in other words, are they qualitative, meaning, okay, that's hot, or is it quantitative, meaning, no, that's 100 degrees C. Okay, so it's depending on how precise our equipment is and what type of data we're actually looking for. So are we just looking to say, heat my food up until it's hot, or put my drink in the fridge so it's cold? Or are we saying, no, heat my soup up until it's 100 degrees C? Okay, so those would be difference in what we're looking for. And based on what type of data we're looking for will affect what type of unit we have, or what type of precision we have. Okay, and if we need a high precision, we're going to use a high precision instrument. If we don't need a lot of precision, we won't use that. We won't use that in equipment. Okay, so just some basic SI units here. Okay, so if the first one is mole, abbreviated MOL, so that just tells us how many of something we have. So I can have 1 mole of something, and we'll talk about what exactly a mole is in a little bit. For length, we're going to use the meter, abbreviated little m. For mass, we'll use kilogram, abbreviated little k, little g, kg. For time, we'll use seconds, abbreviated small s. Temperature will be in Kelvin, just the unit K, not degrees K, just K. For current, we'll amps or amperes for A. And for intensity of light, we'll use candela, abbreviated CD. You probably won't see these last two too much in this chapter or in this class, but these top ones you're going to see a lot. Okay, so some metric abbreviations. Okay, so make sure you have a good handle on these. You're going to need to easily convert between these units. If you're not sure how to convert units with the metric system, make sure that you learn this because you're going to need it a lot. Okay, so if I was you and I was sitting and I didn't quite know the metric system yet, I would either go to a textbook or go to YouTube and just look up a tutorial about the metric system. It's super easy once you get to know it. Okay, but these are just some basic units. Okay, so especially make sure you know the base units. Okay, so King Henry died Monday, don't call me. All of those. So from kilo all the way down to milli, make sure you know all of those. Okay, so kilo, little k, deci, little d, cine would be little c, milli will be little m. And then you get into little bigger ones or smaller ones, you could even say. So micro will be mu, nano will be little n, and pico will be little p. Okay, so you may have so many picometers or so many nanometers. We'll talk about that a lot. Or you could have so many kilograms or so many kilometers. Okay, so these go in both directions. And you'll become familiar with these as we continue along through the class. But do make sure you have a good grip on the metric system because that's what we'll be using. So if you don't quite know it, make sure you get to know it. Okay, so talking about some specific temperature scales here. Okay, so we're going to look at comparing Fahrenheit, Celsius, and Kelvin. And we're going to look at converting between these units. Okay, so the first thing to understand is that the way these systems were developed are basically the same principle. Okay, so we have a Fahrenheit scale, a Celsius scale, and a Kelvin scale. But they're all referring essentially to the same thing. What temperature is something? In other words, how much does it make the alcohol inside of a thermometer move, or the mercury inside of a thermometer move? Okay, and so we just define these a little bit differently. So we're going to start from the Celsius scale. Okay, so the Celsius scale, we said, okay, well, the point in which water freezes, we'll call that 0 degrees C. The point where water boils, we'll call that 100 degrees C. Okay, and so this was based just so that 0 would be the freezing point of water. Absolute 0 then is going to be minus 273 C. And then the boiling point of water will be 100 C. Okay, with the Fahrenheit, we have a little bit different system. So the freezing point of water will be 32 degrees Fahrenheit. So we're pretty familiar with that one. And the boiling point of water will be 212 degrees Fahrenheit. Okay, so notice that the distance traveled in the actual thermometer is very similar, right? So the degree difference is not even remotely the same. So from 0 to 100 is 100, right? From 32 to 200 is a little less than 200. Okay, so they're completely different scales, but they're referring to the same thing. Now, if we jump over to the Kelvin scale, what you're going to notice is that the difference between the boiling point and the freezing point of water, so the freezing point and the boiling point, is still 100 Kelvin. Okay, so 100 degrees C and 100 Kelvin. So it's exactly the same scale. It's just that it's shifted up or down. Okay, so with the Kelvin scale, we wanted to make it so that absolute 0 was 0K, which made, basically we had to sort of bump the Celsius scale up 273 Kelvin. Or just 273, we could just say it that way. Okay, so what that gives us is now our freezing point of water is 273, boiling point of water is 373. Okay, so this makes our conversion really easy. So if we want to get Kelvin from Celsius, we just add 273.15. That's the precise unit there. Okay. But if we want to go between Fahrenheit and Celsius or Celsius and Fahrenheit, we have a little more complicated conversion here. So if we want to get degrees C and we have degrees F, we're first going to subtract 32 from our Fahrenheit degrees and divide by 1.8, and that will give us degrees C. Okay, if we want to get degrees F from degrees C, we'll just sort of undo that formula, and we'll say 1.8 times degrees C plus 32. Okay, so not real difficult conversion, but certainly a little more challenging than just adding 273 to C, to the degree C. Now, if you want to go the other way, so in other words, if we want to solve for degree C, we would just say that this is going to be Kelvin minus 273.15. Okay, so, oh, that should be 273. Sorry about that. Okay, so not a huge deal there. Pretty easy to convert back and forth between those two. Okay, so make sure you get all these conversions straight. So these are something you'll need. So I could ask you, for instance, convert this Celsius units to Kelvin, or I could say, which is the highest temperature, and give you Celsius, Fahrenheit, and Kelvin, something like that. Okay, so make sure you know how to convert between these scales, because we're gonna be needing to do that a lot. Okay. So here you go. Here's our first sort of math-oriented problem to work out. So it says a sick child has a temperature of 40 degrees C. We want to know what's the child's temperature in Fahrenheit and what's the child's temperature in Kelvin. Okay, so here I would ask that you pause the video, and I'll give you some time, and go ahead and work this one out. And then when we come back, I will work it out with you, and we'll see how you did. So I'll give you a few seconds to pause, and then I will start working it out. Okay, so taking a look at this one, we just want to convert a Celsius temperature to a Fahrenheit temperature and to a Kelvin temperature. So the first thing we need to do is we need to pull out our two equations. So we need to be able to convert from Fahrenheit, so just grab that equation, so Celsius to Fahrenheit, so 1.8 times Celsius plus 32. Okay, so all we need to do, take our Fahrenheit temperature, which was 40 degrees C, just plug that straight in here, which gives us 1.8 times 40 degrees C, sorry, that should be degrees C, okay, plus 32. Next, doing that math, you get 72 plus 32, gives you 104. Okay, and that's degrees Fahrenheit, of course. Okay. And to go from Celsius to Kelvin, we just need to add 273.15. So we'll just take our degrees C, drop it in. Okay, so we just take 40 degrees plus 273.15. Okay, so our temperature in Kelvin will be 313.15 Kelvin. Okay, so easy enough. Hopefully those are not too challenging. Just take the temperature you have, drop it in, and just run the math in your calculator. This is a good point to sort of get comfortable with your calculator, whichever one you're using. Hopefully what I need for you to be using is just a regular TI scientific calculator. It can't be a graphing calculator. You don't need it for anything in this class. You just need to be able to crunch numbers like this. Okay, so for the exams and things like that, I only want you using, I think it's a TI-30, something like that. So just a basic scientific calculator. Okay, so make sure you get familiar with that. Okay, so some basic other conversions that you'll need to know. Okay, so get good at things like converting between metric system and the American system. So inches and feet from, it's a meters and centimeters, all that good stuff. The easiest one to remember, this will always get you from inches or feet or meter or yards or whatever it is. The easiest one to me, and this is the one that I remember in my own mind. Okay, so 2.54 centimeters is equal to 1 inch. That's the easiest one to remember. If you can remember that one, you can go from inches to centimeters, and then centimeters to meters to kilometers to whatever you need. Or if you need to go from centimeters to inches, you can. Okay, then you can just multiply by 12 or divide by 12 or whatever it is you need to do. But if you just know how to go from one system to the other, then that's all you need to know. Okay, now for masses and volume, it's not quite so easy. There's not a super easy system for that. The best one I think to remember for that one is just this basic one here. Okay, so go from kilogram to pound. So just remember that 1 kilogram is roughly 2.2 pounds, and you're pretty much good to go. Okay, then you'll have to convert from pounds to ounces and all that stuff on your own. Okay, but if you know how to go from kilograms to pounds, that's a good one to know. And for volume, you'll just have to kind of practice those. These are a little more difficult, but you could go from, for instance, from square inches to square centimeters. That might be helpful. Okay, but you just have to kind of get familiar with these conversions and see which ones you use a lot. And that's kind of how that's going to go. I don't have a trick really for this. It's just something you sort of have to learn and practice. Okay, so density. So this will be our first sort of equation or like derived unit kind of thing that we're going to do. So density. So density is just going to be equal to mass over volume. Okay, so mass over volume. Okay, so it's an intensive physical property. that means is it does not depend on how much of something you have. It only depends on what you have. Okay, so it doesn't matter if I have a big sample, if I have like a whole swimming pool of water, or if I have a few drops of water. Okay, the density of that water is not going to change as long as it remains water. Now there are things that will affect it, okay? But in terms of being at the same temperature, all that good stuff, the density will not change. Okay, the physical properties of mass and volume that determine a substance density are extensive, meaning that they're not dependent on the amount. Excuse me, they are dependent on the amount. So I said that backwards. Okay, so extensive properties are dependent on the amount. In other words, what they're trying to say is if I have a whole lot of water, that's going to have more mass than if I have a little bit of water. If I have a little bit of water, that's going to have a different volume than I have a whole lot of volume. Okay, so those are extensive. But the one in terms of density, those will be intensive. Okay, so intensive, it doesn't change based on how much you have, so that's like density. Extensive, it does change based on how much you have. So it kind of makes sense, right? So if I have a whole lot of something, it's going to weigh more than if I have much less of something. Okay, and densities of liquid and gases are affected by temperature. And that's just because of how much separation we have in the molecule. So how much energy do we put in based on that temperature? How expanded is that gas? How expanded is that liquid? So liquid will change less than a gas, but it will be affected slightly. Okay, mainly the volume is what's going to be affected there. Okay, so just remember that density can be affected by temperature. Most of the time, you're going to be comparing densities at the same temperature. Okay, so you can't really compare densities at different temperatures unless you're looking at the effect of temperature. Okay, so most of the time you'll be at one temperature. So just a real quick calculation here. So that mercury has a density of 13.6 grams per centimeter cubed. Okay, and remember that centimeters cubed is the same as 1 milliliter. Sorry, I can write that a little bit better, I think. Okay, so centimeter cubed is the same as 1 milliliter. Okay, so sometimes you'll hear this called a cc, like in a medical drama. They're referring to a cubic centimeter. It's also equal to 1 milliliter. Okay, so no big deal there. I just want you to know that those are all the same thing. Okay, because you may see them used interchangeably. Okay, so we want to know what is the mass in grams for 95 milliliters of mercury. And it also wants to know in pounds. Okay, so we have a density. We want to know the mass, and we also in grams, and we also want to know the mass in pounds. Okay, so the first thing we want to do is convert from milliliters to centimeters cubed. Why? Because we have 95 milliliters, but our unit here is in centimeters cubed. Okay, remember in this case, 1 milliliter is equal to 1 centimeter cubed. So no real tough calculation there. It's just sort of a one-to-one thing. Okay, next thing, solve for mass at grams using this relationship, and then lastly, convert grams to pounds. Okay, so same question here. So I'll just set up our density equation. Remember, density is mass over volume. Okay, so first thing we want to do, convert our volume in milliliters to our volume in centimeters cubed. So we'll just set up this equation. So in this case, it's just a one-to-one relationship. Okay, so milliliters will cancel with milliliters. We're left with centimeters cubed. But notice it's just one-to-one relationship, so no big deal there. Okay, so 95 milliliters is also 95 centimeters cubed. Okay, now we want to actually solve for our mass. Okay, so the way we're going to do this, remember that we have D is equal to M over V. What we want is to solve for M. So we'll multiply both sides times volume. Okay, so what we have is volume times density is equal to mass. In other words, mass is equal to volume times density. Oh, sorry about that. Sometimes the touchscreen doesn't want to behave the way you want it to. Give me just 1 second here. Okay, So now, once we have this equation, we can just sub in what we know. So sub in our 95 centimeters cubed. Okay. So I'm going to take our density times our new volume, and that will give us our mass. So they've kind of written this out a little bit differently here. So they've written it out this way. So they've written 13.6 grams per centimeter cubed is equal to x over 95 centimeter cubed. Okay, and then just solve for x. In other words, 13.6 grams per centimeter cubed times 95 centimeters cubed is equal to x. Okay, so centimeters cubed will cancel with centimeters cubed, and you're left with basically 13.6 times 95, okay, which would give you 1.29 times 10 to the third grams. Okay, but since we only want to keep 2 Sig Figs, and we'll talk about Sig Figs in just a little bit, but you would report 1.3. Okay, so all you had to do there was just plug in our given volume into the density equation. Using the density and the volume, you can get to mass. Okay, so setting it up this way is probably going to be your best bet, rather than, but I mean, you could do it that way too, just solve for x, whichever way is more comfortable for you. Okay, I'm going to get rid of this just so we can see the next little bit here. Okay, so our last step, we just want to convert from grams to pounds. Okay, so our relationship here is 1 pound is equal to 554 grams. Okay, so grams will cancel with grams, and we're just left with 2.9 pounds. Okay, just simply solving our density equation for the mass, plugging in what we have the density, we have the volume, solve for mass, and then convert that mass to pounds. Hopefully wasn't too tough. Okay, so now a problem for you to try. This one, sort of a long problem to read, but not a super difficult problem to solve. Okay, so it says a man receives a ring he believes to be platinum from his fiancée. Before the wedding, he notices that the ring feels a little light for the size and decides to measure its density. He places the ring on a balance and finds that its balance has a mass of 3.15 grams. And he finds that the ring displaces 0.23 centimeters of cubed of water. And he wants to know, is the ring made of platinum? Okay, so from this, can we determine whether the ring is platinum or not? And one piece of information you're going to need is you're going to need the density of platinum, which I will give to you at the end. Okay, so for now, just solve for what the density of the ring actually is, and then in the end, we'll compare that to the density of actual platinum, okay, and then we'll be able to decide whether it's real platinum or not. So first, take the information you're given and try to solve for the density of the ring. I'll give you a couple seconds to pause, and you can try to work that out. Okay, so let's work this one out. So first piece of information we need is we can say that the density of platinum, I'm going to say the density for platinum, and I just looked this up beforehand. Okay, it's going to be 21.4 grams per milliliter. And that's going to be the same as saying grams per centimeter cubed. Those are interchangeable units. Okay, so since we have a one-to-one relationship between milliliters and centimeters cubed, those are just a one-to-one relationship. Okay, so we have our density formula. So we need to pick out the two important things here. Okay, so we have a mass and we have a volume. So our density formula, we need exactly that. We need a mass and we need a volume. Okay, so all we have to do now is just plug in mass over our volume. So this gives us 3.15 grams over 0.233 centimeters cubed. Okay. So now if you just run that math real quick, so just divide 3.15 divided by 0.233, you're going to end up with a density equal to 13.5 grams per centimeter cubed Okay, so which is not equal to 21.4 grams per centimeter cubed, which is the density of platinum. Okay, so what the question asks us here is the ring made of platinum? So we would say no. We could just say density is too low. Okay, so that's how you would solve that problem. Okay, if you're looking at the slides with everything typed in, this is all typed out for you as well. But I went ahead and wrote it out because I think sometimes that's a little bit preferable. Okay, but I will go ahead and erase my writing so you can also see the type solution without anything on top of it. Okay. Okay, so this next section we're going to talk about significant figures. Okay, so this is going to be used, well, these rules will be used to determine A, how many significant figures are in a number, and B, how to figure out how many sig figs to use when you report your final answer. Okay, so this first little bit will just be a set of rules. Okay, and I'll try to give you several examples of these as we go through, so you can sort of have a good idea what we're talking about. Okay, so the first rule, and the main thing that these rules deal with are whether zeros are important or not. That's kind of the main idea here, the main point, is to know whether a zero counts as a significant figure or not. So the first thing we're going to say is that all non-zero values are significant. Okay, so if it's a number, if it's a digit in a number that's not a zero, then it must be significant. So something like 536 has 3 significant figures. So I have a 5, a 3, and a 6, which are all non-zero digits, so therefore all 3 are significant. The next one. Okay, so zeros between non-zero digits will also be significant. So what we're talking about here is talking about this 0 here in the middle. Okay, these are often referred to as trapped zeros. Okay, so remember, a trapped zero will always be significant. And it's only a trapped zero if it's between 2 non-zero digits. Okay, so they'll always be significant. Next one. Okay, so we have placeholder zeros. Okay, so placeholder zeros to the left of a non-zero digit are not significant. Okay, so we're talking about these zeros up front. These are usually referred to as being leading zeros. Okay, so in other words, it's just telling me, all this is telling me is the same thing as, it's just saying that, okay, no, this 6 goes into the hundreds position. It doesn't go into the tens position, it goes into the hundreds position. And it's telling me that that 4 goes into the thousands position. That's all it's telling us. So if they're to the left of a non-zero digit, they are not significant. And they're often referred to as leading zeros. Okay, the next one. Zeros to the right or after a non-zero digit up to the decimal point are not significant. In other words, notice that these 3 numbers here, or these first 2, do not have a decimal point. Okay, so the number 7,000, so 7000, only has 1 sig fig. The number 32040, this last 0, is not significant because there's no decimal point. Okay, so these are often referred to as trailing zeros, but we have two types of trailing zeros. Okay, so the first type is with no decimal point. So if I have trailing zeros with no decimal point, they won't be significant. So this would be with no decimal point. Okay, the second type I have is with decimal point. Okay, so trailing zeros with a decimal point are significant. So if I wanted to make these zeros significant, I could add a decimal point there. Okay, and that would make all 3 of those zeros significant. But since I don't have that, they are not significant. And then in the last one here, since I have 50.0, this 0 and this 0 would both be significant because of the decimal point. So since I have a decimal point here, that makes them significant. Okay, so two types of trailing zeros, with and without decimal point. Remember, with decimal point, they are significant. Remember, without decimal point, they are not significant. Okay, so make sure you get to know these rules, and we'll do some practice with them. But everything you need to know pretty much about finding how many sig figs a number has are all contained right there. Okay, so that's all the rules really to know. Okay, so here's sort of it's done graphically for you. Okay, so this shows you a non-significant cosmetic zero. So always start a number with a number. In other words, you would write 0 point something. Don't just write 0.0 something. That's not how we write numbers. Okay, so we have non-significant cosmetic zero. In other words, leading zeros. So all of these are leading zeros. So none of those are significant. Here we have some digits that are non-zero digits. So of course this would be significant, this would be significant, and this would be significant. They're all non-zero digits. We have two trap zeros right here. So they're trapped between two 4s. So they would be significant. And lastly, I have some trailing zeros. Okay, so since I have a decimal point, that means that my trailing zeros are significant. Okay, so watch out for your decimal points. Okay, that's going to make your trailing zeros significant. If I didn't have this decimal point, so if I just had this number, so if I forget all about all of these zeros and the decimal point, they wouldn't be significant. But I don't have that. I have this. Okay, so they are significant. Okay, so this is just the rules sort of written in a different way. Okay, so I want to go over them one more time because I think sometimes it helps to hear these rules a couple times and then they kind of, I think, snap for students a little bit better. Okay, so all non-zero digits are significant. So these two numbers both have all non-zero digits. So this one has 4, this one has 3, and all of those will be significant. Okay, rule number 2. Final zeros to the right of a decimal point are significant. So if I have a decimal point and I have trailing zeros, they are significant. So 2.0 kilometers has 2 sig figs, 6.300 centimeters has 4 because of the decimal point. Okay. So rule 3, zeros found between two significant digits is our trap zeros. So since they're between two significant digits, they will be significant. Okay, so these two zeros trapped between the 5 and the 1 are significant, and these 3 zeros trapped between the 3 and the 5 are significant. Rule 4, zeros placed as placeholders are not significant. Okay, so if all it's doing is telling you, sort of scaling where this 3 goes or where this 1 and 7 goes, those are just placeholder zeros. Those will not be significant. So even if I have a decimal point, leading zeros will not be significant unless I had something like this. So if I have a trap decimal or trap zeros, so I have a 1 up front, that would be significant. But since I don't have that, I just have 0.000. Okay, those are not significant. And same thing with 17,000 miles. Okay, those 3 zeros at the end will not be significant. Okay, one more important rule here. If I have counting numbers, okay, or constants, these have infinite sig figs. So something like pi, for instance. Or if I'm saying 1 inch is equal to 2.54 centimeters. Those have an infinite number of sig figs. In other words, they wouldn't narrow down how many sig figs you do in a calculation. Okay, so this next problem, it just wants us to count up how many sig figs or determine how many sig figs are in each number. Okay, so we'll just walk through these together. Okay, so the first one, we have 4.501. Okay, so I'll give you a second to think about those ones. So try to grab a pen and paper and write down how many sig figs you think each number has. And that'll give you an idea whether you're correct or not. Okay, so we see that we have 3 non-zero digits. Okay, so we know it has at least 3. So the only thing we really have to figure out is this 0 in the middle. Okay, well, we know we have a trap 0, so this is going to have 4 sig figs. Next one, 400, 400. How many sig figs are this one? Okay, so I have 2 trailing zeros and no decimal point. So this would be just one sig fig. Since trailing digit zeros with no decimal point are not significant. Okay, 2 zeros after the 4 are just placeholders, in other words. Okay, 0.0040. Okay, so how many sig figs? First thing I see is I have these leading zeros. Okay, so those are just placeholders. They don't serve any purpose other than holding the place of that 4. So those are not significant. So I'm just going to draw a line through them. Now I have a 4, non-zero digit, so of course. And then I have a trailing 0, but I have a decimal point. Okay, so this is going to be 2 sig figs. Okay, so 3 zeros in front of the 4 are just placeholders, so they're not significant. 0 following the 4 is significant since I have a decimal point. Last one, 4,101. Okay, so this time I have a comma. Okay, so this one is a little bit tricky. And the reason why is based on how we would read it in the US versus maybe how someone in Germany or in Russia might read this number. So what we would say for this number, we could say it has 4 sig figs. So if we're in America, we would say it has 4 sig figs. Okay, but if we're somewhere else, the comma is sort of confusing. Okay, and we'll get to the reason why in just a little bit, but commas get a little bit tricky, and we'll see why in just, I think, in the next slide. Okay, but this would have 4 sig figs. As long as you're reading it in terms of the US way of reading it, this would be fine. Okay, next one, 0.400. So how many sig figs? Okay, the 0 up front would not be significant, just a placeholder. And the 2 zeros at the end would be significant since I have a decimal. So overall I have 3 sig figs. Okay, give you just a second there. Okay, so sig figs in scientific notation. Okay, so for the most part, we're going to be using scientific notation pretty much with every number, meaning we're going to be putting it into this times 10 to the power notation. Okay, so we're going to pretty much want to convert all of our numbers to scientific notation. One of the reasons why we do this is to remove ambiguity in our numbers. So based on how many sig figs we can have, we may want to convert to scientific notation just to get rid of some ambiguity there. So if we wanted to convert 3010 scientific notation, so always remember we have an unwritten decimal here. So we go 1, 2, 3 places to the left. So it would end up with 3.01. So our new decimal goes between the 3 and the 0. And then times 10 to the power. And the power is going to be based on how many places you move that decimal point. So we moved it 3 places to the left. So we'll have a positive 3. Okay, so we moved it 3 places to the left. So we have 10 times, or 3.01 times 10 to the third power. Okay, so what if I wanted to go the other way? So what if instead I had a small number that I wanted to turn into scientific notation? Well, this time I have to move it 2 places to the right. So this time I have a negative 2. So times 10 to the minus 2, because I moved the decimal to the right. Okay, so what I'm doing here is I'm trying to take my number, and I want this leading number to be between 1 and 9. Okay, so at 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3 is both perfectly acceptable. Okay, and what this does is it allows me to have some control over how many sig figs I write. Okay, so I can choose to round this number depending on how many sig figs I have in my calculation. So if I didn't, for instance, have 3 sig figs in this number, I might not write that 0. Okay, but this is just for the purpose of conversion. Okay, so make sure you get a handle on scientific notation. If you're not familiar with this, or maybe it's your first time seeing it, again, go to textbooks, go to YouTube, find something, some kind of primer that will help you do this. But it's really not, again, not too complicated once you get the hang for it. You're just moving a decimal point around and really just knowing whether the sign should be positive or negative is the only kind of trick there. Okay, so if it's a big number that you're making small, your power should be positive. If it's a small number that you're making bigger, your power should be negative. Okay, so just remember those two things and you should be good to go. But the important thing here is that both of these numbers now we're displaying with 3 sig figs. Okay, so this first one here we had 3. Okay, but it wasn't in scientific notation, so we moved it over, and we still have 3 sig figs because that's how many we want to keep for our answer. Okay, but the important thing here is it's easier, okay, to show how many sig figs I have. So maybe if this 0 was significant, I would write 3.010. Now I would have 4 sig figs. See what I'm saying? So instead of having to add a decimal to this number, I can convert it to scientific notation and show easily how many sig figs I have. And here I have 3, and that was easy enough to keep 3. So that kind of didn't change. But you can kind of see what I'm saying there. So it's an easy way to show or to write numbers and show exactly how many sig figs you have if it's maybe kind of an ambiguous number. Okay, so the next section we'll talk about is significant figures and measurement. Okay, so when you're reporting the significant figures in an answer, it's dependent on the precision of the measured values given in the problem and determined by the precision of the laboratory glassware you use. In other words, if you're just solving a problem from the book or something like that, or on an exam, the level of precision you report will be based on the numbers you're given. If you're actually solving a problem in the lab, it will be based on the type and the precision of the glassware that you use. Okay, and just remember that if we have conversion factors, we're going to consider those to be just exact numbers. In other words, they have an infinite number of sig figs. Okay, so all your conversion factors are going to have infinite number of sig figs. So an example would be going from inches to centimeters, pennies to dollars, or saying that 12 is 1 dozen. Okay, so we have another set of numbers here, and we just want to determine how many sig figs are in each. So go ahead and take some time, pause the video, and try to tell me how many sig figs are in each of these numbers. Okay, so let's look at A. So A, we have 2 leading zeros, and we have a trailing 0. Okay, but we do have a decimal point, so these first 2 are not going to count since they're leading zeros. But I have 1, 2, 3, 4, and the trailing 0 will count since I have a decimal point. So A is going to have 4 sig figs. So 1, 2, 3, 4. Again, sometimes the touchscreen doesn't do quite what you want it to every single time. Okay, so let's look at B. Okay, so B, we have 5.0003 when it's in kilometers. Okay, so we have 3 trapped zeros, but since they're trapped between a 5 and a 3, of course those will be significant. Okay, so that's going to be 5. In C, we have 10 decimeters. Okay. So that trailing 0, since we don't have a decimal, won't count. But since it's a conversion factor, we actually have an unlimited. So remember that conversion factors are infinite. So since we have 10 decimeters equal to 1 meter, okay, so we have unlimited. Okay, letter D, we have 1.00 times 10 to the 5th seconds. Okay, so we have a 1 point and then 3 zeros, so that would be a total of 4. Okay, so notice that this part you don't include. So it would just be 1, 2, 1, 2, 3, 4. Okay, so you don't include the scientific notation when you're counting up the sig figs. Next one, E, we have 1, 2, 3, 4, 5, 6, or 5 or so leading zeros, but remember, none of those make any difference. So this is just 1. Okay, and then letter F. So this one I said with the comma might be a little bit tricky or confusing. So one possible answer for this is it could be 1. Another possible answer for this would be 4. And depending on where you're from and what system you're using, your answer might be different. And the reason for that is that in places like Russia, for instance, or in Germany, I believe, they read this the same way we would read this. Okay. In other words, they use the comma as the decimal point instead of the other way around. Okay, so we would label this as being ambiguous because it could either have one sig fig, so only this one up front could count, or the whole number could count. And depending on who we are and where we're from, we may count this up differently. One way to remove ambiguity could be to add a decimal point, or it could be to not use the comma. Okay, but one possible answer for this, and the answer I would give if it was my, on my exam or something like this would be ambiguous. Okay, so we don't know how many sig figs we have because we don't know who wrote that number. I don't know if that's 10,000 meters or if it's 10 meters. Okay, so you want to avoid that. And the way you could avoid this is you could just say 1 times 10 to the 1, 2, 3, 4, fourth power. Sorry, that's a 0. Or if you wanted to say, no, I have all of those sig figures, you could say 1.0000, 1, 2, 3, 4, 1, 2, 3, 4 times 10 to the 1. Okay, so you can remove the ambiguity by just adding scientific notation. Okay, so the answer there would just be ambiguous. Okay, so now we know how to find how many sig figs are in a number, but what if we're doing math? So how do we know how many sig figs to report when we're actually doing a calculation? Okay, so that's what we're going to talk about. Okay, so if we're doing mathematical operations, the type of operation will dictate how many sig figs we report. Okay, so if we're doing multiplication and division, you're going to go with the least precise measured value. In other words, you're going to look for the number that has the fewest number of sig figs, and that's going to determine how many sig figs you report in your answer. And we'll do some examples of that. If we're talking about addition and subtraction, it's the value with the smallest decimal measurement determines the sig figs. Okay, so you're going to look for the number that has the fewest sig figs after the decimal, or just the fewest numbers after the decimal. Okay, and that's going to determine your sig figs. Okay, so first let's look at multiplication and division. Okay, so we would say 3.56 times 4, and our calculator would tell us something like 14.24 centimeters cubed, or squared, excuse me. But we only want to report the fewest number of sig figs in any one number we have. So here we have 3. Okay, so this is 3. And here we just have 1. Okay, so we would actually report our answer as just 1 sig fig. So we could report this as 10 centimeters, or we could write it as 1 times 10 to the 1 power centimeters. Those would both just be 1 sig fig. Okay, but because we're doing multiplication, since this only has 1 sig figs, it dictates how many sig figs we have in our answer. Okay, the next one. Okay, so similarly, we're doing multiplication. So we have 2.050 times 5 milliliters. Okay, so your calculator would tell you something like this. But again, we want to search for the number that has the fewest number of sig figs, which would be 5.0. So this has 1, 2, 3, 4. This only has 2. So we're going to report our answer with just 2 sig figs, so 1.0 times 10 to the first. Okay, so we're just rounding that number off to give us the correct number of sig figs. So here, we rounded to just 1, so this became 10. Here we rounded to 2, so this became 1.0. Okay, what about division? So same rule. So fewest number of sig figs. So here we have 45 divided by 9, which of course gives us 5. Okay, but we want to report only 1 sig fig, since 9 only has 1 sig fig. So we would report it just as 5. Okay, D, we have a couple steps here, but they're all multiplication. Okay, so we have 4.5 feet times 12 inch over 1 foot. We have 2.54 centimeters over 1 inch. And that's going to be equal to 1 meter over 100 centimeters. Okay, so if we look at this, these are all conversion factors except for one. So this is infinite, and this is infinite. Okay, so our answer is going to be based on this first one. So 1.3716, we would round to just 2 sig figs, or 1.4 meters. Now, with addition and subtraction, we have a little bit different method that we use. Okay, so we want to line the decimal points of the numbers up. Okay, and then you'll do your addition or your subtraction just as you normally would. The big difference here is what you want to do is you want to search for the number that has the fewest number of sig figs, and you want to draw this line, okay, this red line. And that's going to tell you where to chop off the sig figs. In other words, it's going to tell you where to round. Okay, so you do your addition like normally. Okay, then draw the red line, or with your pencil, it doesn't have to be red. Okay, and that will tell you where to round the number. So we would round to this 7. Okay, so that would go up to an 8, so our number becomes 336.68. Same thing with subtraction. So even if your decimal is imaginary, so we have an imaginary decimal there, go ahead and line it up. And again, draw the line where you have the fewest numbers after the decimal. Do your subtraction as normal. Okay, and this is telling us we have to chop off the entire decimal places, since the first number has none after the decimal. So we can still keep these 3 sig figs up front, but we're going to chop off our decimal part. So we round to this 6. Okay, so our answer just becomes 456. Okay, so now I have a couple for you to try. So try these A through D, see how many sig figs you report in your answer, and see if you can report the correct answer. Go ahead and pause the video for a second, work these out, and when you come back, we'll go over them. Okay, so let's take a look at A. So I'll actually just write these out right here below. Okay, so for A, we have 1.10 times 0.5120 times 4.0015 divided by 3.4555. Okay? And you could just punch this into your calculator. So remember, do your multiplication first, then your division. So remember, please excuse my dear Aunt Sally. So multiplication before division. Okay, remember that. Okay, so go ahead and do your multiplication. So you multiply all those numbers, then divide by 3.4. And you would end up with this number. So 0.0, it's reading my hand for some reason. Sorry, 0.65219. Okay, now we want to try to figure out how many sig figs we can actually report. Okay, so just look here. This has 3. It's 1, 2, 3, 4. This has 1, 2, 3, 4, 5. This one has 1, 2, 3, 4, 5. 1, 2, 3, 5. So we want to go with the smallest, which is 3. Okay, so we would round this to just 3 sig figs, which means to the 2. So we would report 0.652. We don't have a unit here. Okay, so that's our answer. With B, okay, now we have some addition. So we're going to want to line this up. So they've written it kind of nicely for us, but I'm going to rewrite it. 3.55. Keeps wanting to read my hand. I usually don't have that problem. Okay, so again, line up your decimal. So 1501. I know I'm writing that a little bit weird. I'm just trying to keep my decimals lined up. And lastly, so this is plus and this is minus. And normally you wouldn't do this in this order necessarily. You wouldn't stack these up. This is just sort of to show you the process. So you could do these separately if you wanted to. You could do them together like this if you wanted to. The important thing is that you understand how many sig figs to report in the end. Okay, so if you do this addition and subtraction, you end up with 4.8730. So it's important to try to keep your numbers lined up as best you can. So now we want to decide, where do I round this number to? So I would draw an imaginary line. That tells me to round to this 8. So I would report my answer as in this case 4.9, since the 7 tells me to round up. Okay, so for C, we have a mixture of multiplication, division, and subtraction. So the first thing we want to do is we want to just manage which order we should do these in. Okay, so with this first first thing I want to do with C is I want to do this parentheses first. Okay, so I have some subtraction here. Okay, so I'm going to go ahead and just do that for us real quick. So we end up with 4.562 times 3.99870. And then this number at the end here is going to end up being 0.3455. Okay? And so what we want to know here is, where do we actually stop this number? Okay, so if we were to line these up, this only has 2 numbers after the decimal, so we would only keep 2 since that's the fewest. So we would actually round to here. And I'm just going to draw a little line there because that reminds me that this number actually only has 2 sig figs in it. It doesn't have all of those. It only has the 2. So the best way to indicate that is just with a little line. Okay, then go ahead and do the math as you normally would. So you end up with this 52.79904. Okay, now find the number with the fewest sig figs. This has 4. This has a lot. 1, 2, 3, 4, 5, 6. This only has 2. So we're going to keep the 2. So I'm going to round to this 52, to the 2. So my answer becomes, so I'm going to round the 2 up. So this becomes 53. Okay, the last one, D. Again, this is another mixed one. Okay, so here I'm going to say, do the parentheses first. Okay, so I'm going to end up with 8.162 minus 8.02. I need to figure out where to round this first number. So I'm going to look in the parentheses and see that this only has 2 sig figs. That tells me this stops at this 1 actually. Okay, so then I'll finish doing this. So my answer becomes 0.142. Okay, now I have to figure out where to round my answer. So I look and I see, okay, well this one actually only has 1 after the decimal, so that means I have to stop at 1 after the decimal and 1 after the decimal. Okay, so my number becomes 0.1. Okay, so if you have more than one type of problem within the same problem, you just sort of follow your order of operations and just remember where you would actually be rounding numbers. You can use that little line underneath it, and that should help. Okay, so that's how you do it. If you have multiple steps, you just follow the procedures in order. Okay, so the last, second to last topic we'll talk about in this chapter, and we're almost done. We just have a little bit left to go. Okay, so we're going to talk about precision and uncertainty. Okay, so precision is the agreement or closeness to repeatable values. Okay, so you can be precise but not accurate. Okay, but this is how close or the agreement of the values. Okay, so how repeatable is it? Okay, so can I take the same measurement over and over? Accuracy is the agreement or closeness to the actual known value. So this just tells me, precision tells me, can I get the same number over and over? So is it repeatable? That's the key here. Precision is repeatable. Okay, accuracy tells me, how close is it to the actual known value? Okay, so if 1 meter is 100 centimeters, but I'm measuring 99.99999 centimeters every single time, or I'm measuring 80 centimeters over and over. So if I said 1 meter and I kept measuring it as 80 centimeters over and over, that's precision, but it's not accurate. I have another example for you here too that will probably be a little more clear. But just remember, accuracy is how close is it to the known value. Precision is how repeatable is it. Okay, and this is often reported as an uncertainty or a confidence factor. It's the degree of measurement, or how much the measurement differs, and it's usually reported as a plus or a minus. So you may see that out to the side of a number. We're not quite there yet in this class, but just know that it's coming. Okay, so this is usually found using statistical methods, and you'll see numbers like this. So you'll see 23.45 plus or minus 0.05, and that's going to tell you the level of confidence. In other words, what this means is that that number could either be 0.05 higher or 0.05 lower. So So it's like the tolerance factor you may have heard before. Okay, so we'll get to that a little later in the class, but just understand that's what that number means. So if you see a plus or a minus outside a number like that, that's what they're talking about. So it just tells you how confident that number they are. In other words, it's kind of like how good are the Sig Figs they're reporting. That's kind of one way to look at it. Okay, so this example might be a little bit easier to understand. Okay, so we'll talk about precision versus accuracy again. So if we're throwing darts at a target, okay, we want to look at how accurate and how precise we are. Okay, so the first one, this top left one. Okay, so here we're throwing darts and we're hitting just all over the board. So we don't have a good grouping, we don't have any kind of accuracy. We have one in the bullseye, we have one all over the place. Okay, so this will not be accurate, okay, because it's not close to the bullseye. So the closer we are to the bullseye, the more accurate we are. And we're also not precise. And the reason we're not precise is because we don't have any repeatability. Okay. Now the second one is one in the top right corner. Okay. So here we have low accuracy. Okay, so we're far away from the actual bullseye. Okay, so this is what we were aiming for. We're aiming for the bullseye. But we have them all together, so it was repeatable. So we have low accuracy, but we have high precision. Okay, now in the bottom left. Okay, so now we have high accuracy because we're all sort of close to the bullseye. But we have low precision because they're still sort of scattered. We don't have a nice grouping. Okay, so it's low precision because it wasn't repeatable, but higher accuracy because they're all closer to the actual value. And in the bottom right, we have high accuracy and high precision. Okay, so they all hit the bullseye and they're all clustered together. So that's both high accuracy and high precision. Okay, so hopefully that sort of helps understand the difference between precision and accuracy and what's high precision, what's low precision, and you kind of get the idea there. Okay, so what if we wanted to look at this with actual data? Okay, so here we have 3 sets of data. So we have 3 students. Okay, so we're all trying to measure a 10-gram mass. Okay, we're going to look at the results and we're going to decide, are they accurate and are they precise? Okay, so the blue line represents the true mass. Okay, so if we look at student A, they have a measurement of 10.49, 9.79, 9.92, and 10.31. Okay, so they're all pretty far off from the true mass. Their average is about 10.13. Okay, so they're all pretty far off from the actual value. Okay, so those would be inaccurate. And there's no consistency, so they'd also be imprecise. So the data from student A would represent accurate or data that was both inaccurate and imprecise. Student B, okay, so they're measuring the same 10-gram mass, so maybe they have a different balance, or maybe they use a triple beam, maybe student A used a kitchen scale, maybe student B used a triple beam, who knows, okay? But let's look at student B's data. So they have 9.78, 9.82, 9.75, 9.8. So on average, it's close to 9.8. Okay, the important thing to look at here is, yes, they are off from the known value. So remember, the known value is 10 grams. So they're not accurate, but they're getting relatively repeatable results. So that means they're precise. Okay, so they're getting the same result, so they're precise in their measurements, but they're inaccurate because their answer isn't right. Okay, the one on the right, we have student C. Now maybe student C is using a, analytical balance, a high precision analytical balance. Okay, so they take the same 10-gram mass, they put it on there 4 times, and look what they get. They get 10.03, 9.99, 10.03, 9.98. So an average of very, very close to 10, 10.01. Okay, so this example of data that's both accurate because it's close to the true value, and it's precise because it's repeatable. Okay, so student C would represent accurate and precise data. So you want to be like student C. You want to have accurate and precise data. Okay, so just finishing up on this idea of this topic of precision, and we're almost done with the chapter. We're going to go a little bit over with this video, but we'll be done very quickly after this. Okay, so this idea of the last digit on a scale. Okay, so for every instrument you have a degree of precision, and that precision varies from whether it's something like a kitchen balance or kitchen scale like we have up top, a triple beam balance, or maybe a analytical balance, so highly precise balance. And basically the way, or it could be a thermometer, it could be a burette or a graduated cylinder. And basically what we're talking about is that you can estimate a final digit. So I'm just going to draw a scale out here. So if I had something like this, maybe. Okay, so say this is 0 ml and this is 10 ml. Okay, so maybe I'm using a graduated cylinder. This would be an example maybe of a beaker. Okay, so suppose I had a level of liquid in this beaker that was right about here. Okay, so if it was halfway, I could say that, okay, well maybe this is 5 ml at this point. Okay, but it's not 5 ml. Okay, it's somewhere between 5 and 10. So maybe I estimate this is about 7 ml. Okay, because that's all the precision I have. So I can't really estimate another digit here, because that's just all the accuracy I have. I'm honestly estimating that digit to begin with. Okay, but so what we're talking about here is what then if I go in and I divide each of these into, so now I have 5 ml. And now in between each one I have 1, 2, 4, 5, 6. So I have 10 little marks. I can't really fit 10 in here. Maybe I can do it up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I made them too far apart. But just for the purpose of illustration, hopefully you can see what I'm talking about. So now I have not only, well, I should make these 5 actually. That would be better. Sorry, I'm kind of doing this on the fly, so just bear with me. Okay, so here I have 10, there I have 5. Let's put 5 marks in between. Okay. So now I can say 5, 6, 7, 8, 9. So I only put 4 there. All right, and then that would be 10. Okay, so just bear with me here. So I should only put 4 here, is my point. Okay, so hopefully I'm not making this more confusing. Okay, there we go. Okay, so now if I wanted to read this, I could read this number as being, well, it's 6. I know it's at least 6 ml. Okay, so it's 6. But now I can estimate one more digit. So I can say, okay, well maybe it's close to that 7. So I could say maybe this is 6.8 ml. Okay, so this 8 is the estimated digit. And by dividing these more, I'm giving the piece of equipment more precision. And you can see that on these two scales, these two balances. So if you look close at this one, you can see there's lots and lots of divisions. And on this one, there's only a few divisions. Okay, so the more divisions I have, the higher precision I have. Okay, and if I was to come in here and in between these, put even 10 more marks. Okay, well then I could say, okay, well now it's 6.8, and now I could do one more, 5. So you can always estimate one more digit past the accuracy you have. And depending on what piece of equipment you're using, that's going to vary how much precision you have. Okay, so that's the takeaway here. The more markings you have on an instrument, more precision you have. Okay, so the more Sig Figs you can report. If you have less precision, you report less Sig Figs. And your first lab will deal with this. Okay, so it'll go in more detail with you there. Okay, but that's the general idea. Okay, so this will be our very last topic, and then there's some problems for you to work out at the end. I will post up the answers for those, and if you have any trouble solving them, I'm going to show you a method on one of them. If you have any trouble solving them, please feel free to contact me, or to go check out the SLC as well. Okay, So the last thing we're going to talk about here is called dimensional analysis. Okay, so this is a process for solving problems where you're either converting units or using your units to sort of guide you through the problem. Okay, so that's we call dimensional analysis, and I'm going to show you one example of this, and I think you'll pick it up pretty quickly. It's really not too tough. Okay, so many problems in chemistry involve the relationships to convert one unit to another. So maybe you're converting from, I don't know, quarts to gallons or something like that. Okay, so you can use dimensional analysis to do that. Okay, so you're going to use conversion factors, which are the relationships between two units. Okay, and these conversion factors can be based on, okay, I need 1 mole of this and 2 moles of that for a reaction, or it can just be based on 1 inch is 2.54 centimeters. So it just depends on, what you're actually doing in the problem. Okay, and these can be exact or measured. Okay, and generally they're given as these kind of equivalent statements. So 1 inch is equal to 2.54 centimeters. The more useful way to use this is to say 1 inch over 2.54 centimeters. Okay, or 2.54 centimeters over 1 inch. This is the way we're going to use them, and I'll show you why in just a second. I think it will be crystal clear. Okay, so basically you're going to arrange the conversion factors so that the starting unit cancels, and so that you end up with the unit you're looking for. So you can string many of these together, okay, and end up with the right answer without having to do several calculations. Okay, so basically it looks like this. So take a given unit, multiply by the conversion factor, put into that sort of fraction form. Okay, so the units cancel, and you end up with the unit you're trying to find. Okay, we're going to use this lots and lots in chemistry. So for instance here, we want to convert feet to inches. Okay, so our conversion factor is that there's 12 inch per 1 foot. Okay, so we're just going to multiply 2 times 12 and then divide by 1. Okay, so feet cancel with feet, and we're left with inches. Okay, so 24 inches, of course. Okay, and you can go through this little bit of a plan on your own. I just want to show you how to solve one, and then I think you'll really won't have too much trouble with this. Okay, so this problem wants us to convert 1.76 yards to centimeters using dimensional analysis. And this is given that 1 inch is equal to 2.54 centimeters. Okay, so the way we're going to do this is we're going to start from what we're given. So we're given 1.76 yards. And I'll try to write as neatly as I can. 1.76 yards. Okay, and we're going to set up these little train tracks. So this is the way I learned to do it. This is the way I prefer to do it. I'll show you sort of the translation of this. That might help it make sense if it doesn't quite click. But let's see how it goes. Okay, so 1.76 yards. Okay, and we want to eventually get to centimeters. So the best thing to do would first be to convert yards to inches. So I know that in 1 yard, I'm just going to put YD for yard. I'll put that up here too for consistency. So 1 yard is equal to 36 inches. Okay, now why did I do it that way? Why didn't I say 1 yard over 36 inches? Well, the reason I did that is because I want yards to cancel with yards in the end. Okay, so that's one conversion. Now I can draw a line and I can do another conversion. So now I can say that, okay, well, I want centimeters, and I know that there's 2.54 centimeters per 1 inch. And again, why did I put it that way? Why didn't I write 1 inch 2.54 centimeters? Because if I did it this way, inches would be left uncancelled. So I don't want to do that. Okay, so what I want to do here is I want to be able to cancel inches with inches, and I'm left with centimeters. Okay, so now I can say 1.76 times 36 times 2.54 divided by 1, and then divided by 1, which of course you don't have to do divided by 1. Okay, and this gives me 160, oh, that's a tiny 6, 0.877, and I would of course want to round this with good Sig Figs, which I would only, this is infinite, I only have 3, so I would round to 161 centimeters. Okay, that would be my final answer. So the sort of translation that I'm talking about here is what this means is, so I'm saying 1.76 yards times 36 inches over 1 yard times 2.54 centimeters over 1 inch. And that's going to give you the same answer. Okay, so you could do it this way. So you could do, 36 divided by 1, 2.54 divided by 1. Obviously, that doesn't really impact the numbers in this case, but sometimes this number will not be just a 1, it'll be a 3 or something. Okay, or it could be the other way around, for instance. Okay, so you can do the division first and then multiply, or you can multiply straight across the top and then divide by everything on the bottom. And those two will give you the same answer. Okay, so that's just the basics of using dimensional analysis. And there's several more problems for you to do here, but I'm going to let you work those out, and I will put up the answers for you. And if you have any trouble with those, please let me know. Let's see here. So here's another one. So you want to convert 1.8 quarts to cubic centimeters using dimensional analysis. Okay, and here's another. Just calculate displacement, basically converting between liters to cubic inches. Okay, and then here at the end, there's a couple problems for you to solve just using some basic equations. Okay, if you have any problem with these, please feel free to email me. We can meet for office hours. I think these are pretty straightforward, so go ahead and give them a try. And if you do have trouble, either see me, see the SLC, and we'll be more than happy to help you with those. I will post some worksheets up on dimensional analysis and Sig Figs for you guys, so if you want some more practice, you can do those. Okay, but that's going to end this chapter, and we will pick up next time.